The Big Bang Theory has been refuted by the results of the James Webb Telescope. With the help of a single magnificent picture, the James Webb Space Telescope has recently made an incredible discovery that is appending long-standing arguments and leaving scientists in disbelief. The Internet's most recent discovery is both aesthetically stunning and a game-changer that threatens to completely alter how we see reality. Thus, the age of conjecture is ended. What ferocious scientific argument has this picture definitively ended? How is the breathtaking image taken by the James Webb Space Telescope altering our perception of the universe? Join us as we explore why James Webb's discoveries are ending physics discussions with a shocking picture. The main problem with astrophysics is that scientists are unable to agree on the age of the universe and its rate of expansion. For generations, this unexplained phenomenon has baffled scientists, inspiring them to undertake rigorous study in an attempt to uncover solutions. The study of cosmology aims to comprehend how the universe was formed, how it is assembled, how it has evolved throughout time, and how it will finally end. The recognized cosmological model in this discipline has evolved significantly during the last 100 years. The Hubble constant, which indicates the speed at which the universe is expanding, is a measure of the universe's expansion. Although measurements of the Hubble constant are not simple, they can be broadly divided into two groups. The Big Bang Theory suggests that the universe has been expanding from a very hot and dense initial state for about 13.8 billion years. Observations made locally and in the early universe include studying celestial bodies such as variable stars and type Ia supernovae, which serve as standard candles for measuring the Hubble constant. By determining how the universe's expansion affects these objects' speeds, scientists can ascertain their distances and, ultimately, the Hubble constant. The second group involves measuring the microwave radiation of the early universe through observations of the cosmic microwave background radiation, CMB, which is the afterglow of the Big Bang and was discovered in the 1960s. By measuring the minute temperature and polarization variations that the CMB radiates, scientists can display the microwave radiation of the early universe at an age of 380,000 years. The issue is that although astronomers can determine the age of the universe and its rate of expansion due to these discrepancies, the conclusions of these two approaches do not agree with the results of local observations. Local observations show that the universe is expanding faster than our estimates based on CMB data. More study is being done to find out more about the current mysteries of the cosmos as scientists have been working hard to determine the causes for these outcomes. Since the James Webb Space Telescope can display the faintest and most distant elements of planets and galaxies that we would not have thought possible to see due to its abilities, the difference in measurements indicates that either new science we do not yet know about or mistakes in one or both ways by which we are measuring things. Scientists naturally assumed that data from the James Webb Space Telescope would assist us in precisely calculating the Hubble constant. However, the first wave of data has remarkably made matters more complicated. It has given us new insights that are not coherent with what we thought we knew. Could this data lead to a new theory and revolutionize how we think about space? If so, we might need to review our understanding of how the universe works. For instance, we may discover particles and forces that have never been observed before, or it could signify that dark energy, an unknown factor responsible for the accelerating expansion of our universe, needs to be re-examined. So far, the ways we think about space have evolved as we continue to discover new things. For example, in 1965, when researchers discovered the cosmic microwave background radiation, it served as strong evidence for the idea of the Big Bang Theory. Before then, scientists thought that the universe was eternal and hence was constantly expanding at a uniform rate. But the new evidence proved that was not the case. Also, when we found out towards the end of the 1990s that the universe was continuously expanding at an accelerating rate, it further changed our understanding. We discovered dark energy and its influence on the universe's expansion. Thus, every time we learn something new, we question whether it fits into our current framework. If not, we come up with new approaches to understand the universe better. To this end, the issue we are facing in cosmology today might lead to the discovery of the most wonderful solutions to the universe. While the issue is challenging, it is also exhilarating as it compels us to develop more technologically advanced tools to explore space. This cosmological dilemma also unites the scientific community from different countries, as every scientist wants to know more about the universe. Most importantly, it shows that science is constantly changing and growing as we learn more about space. Along with the Hubble tension, there is also a concern known as the S8 tension. This is with regard to the spatial distribution of matter in the universe. This can be used to draw a structural picture of the universe and see how it has evolved. Astronomers refer to this phenomenon as lumpiness because there are areas of space that have lots of galaxies closely grouped while other areas are sparse. Scientists will use different techniques to measure this lumpiness, and one way is to look at how the light from distant galaxies gets bent by the different gravity of big objects such as galaxy clusters. Because dark matter is invisible and does not emit light, gravitational lensing gives us a means to investigate its location. Researchers can also use the cosmic microwave background, CMB, an afterglow from the Big Bang that has been in motion for about 13.8 billion years and can reveal information about the early universe. Scientists can figure out how the cosmos was lumpy when it first started, which should explain the observed lumpiness of the universe now on a big scale. But here's the catch. These findings also contradict the CMB's lumpiness predicted by the non-spherical gravity distribution model, which suggests that the early universe's matter distribution was more homogeneous than the distribution observed through gravitational lensing. As a result, we can speculate that there may be additional factors that the explanation does not take into account, which returns us to the dark matter conjecture. The question of what dark matter is and how it works is still unanswered, but there is still hope because the James Webb Space Telescope, JWST, is poised to revolutionize astronomy with its unparalleled sensitivity and resolution. The telescope will study the early stages of the universe and look into the formation of the first galaxies and stars, which will allow for more accurate measurements of cosmic expansion and matter distribution. Whether the solution involves learning more about dark energy, uncovering entirely new physics, or even improving our comprehension of dark matter behavior, these important questions will require exact observation and perhaps novel theoretical approaches to be answered. The implications will be far-reaching when it comes to unraveling the secrets of the cosmos. Scientists operating in blindfolds may be compared to meticulous investigators who are fixated on finding the answers using one of the most highly regarded supercomputers in the world located at Durham University in Britain. NASA's most recent project, Flamingo, is evidence of the agency's growing passion for scientific exploration. Project Flamingo is an incredibly impressive achievement in the world of computational progress. It requires more than 50 million hours of computer time. The experiment, which involves 30,000 processors in all, demonstrates the scientific community's commitment to investigating the cosmos as a whole, with a primary emphasis on dark matter. Scientists are still fascinated by dark matter, the enigmatic substance that neither emits, absorbs, nor reflects light, but is assumed to exist because of its gravitational pull on visible matter. Project Flamingo takes a different approach from earlier simulations in that it uses a systematic method to include all potential cosmic elements, from stars and black holes at the center of the universe to galaxies with a wide variety of gas contents. The fundamental landmark drawing served as the starting point for the progressive change in the universe's depiction, and it is evident why complex projects like Project Flamingo were undertaken. Cosmic disputes, in which the measurements seem to be inaccurate and do not fit the universe's structure, imply a basic misinterpretation of how the universe functions as it is now understood. If these metrics were musical genres, they would be comparable to jazz and classical music, each with a unique technique but still connected. Flamingo aims to bring these disparate viewpoints together and sharpen our individual perceptions of the cosmos. But despite its sophistication, the cosmic tension persisted. This tension serves as sobering evidence that we haven't fully solved many of the mysteries surrounding us. The universe doesn't seem willing to share its secrets with us in this way. Every time we add a new data point or simulation model to our toolbox, a new vast universe opens up with new problems to solve. It's a never-ending quest. Since Edwin Hubble's groundbreaking discovery of the expanding universe in the early 20th century, scientists have made a staggering number of discoveries about the nature of the universe, including the Big Bang theory, dark matter, and dark energy. They have also examined the cosmic microwave background and painstakingly recorded the positions and velocities of the galaxy at ever greater degrees of refinement. Each of these milestones is like discovering a crucial piece of the cosmic puzzle, which has led to a desire to learn more and work toward a deeper understanding of the cosmos. The universe is shrouded in mystery, and it may be detrimental to reveal its realities too soon. At each investigative step, expert hypotheses are presented by scientists, revised models, and further clarifying questions. This is similar to how the Big Bang Theory's notion was previously hotly debated but is now accepted as a basic component of scientific knowledge. Dark matter is no longer just a theory but a fully realized, fascinating piece of our cosmic puzzle. The finding of dark energy, an unidentified force pushing the universe's expansion, was a late 20th century revelation and is now firmly established. Science is not static. It evolves with each discovery, expanding on what we previously understood. Thus, cosmological research will continue with advanced telescopes, sophisticated simulations, and a devoted scientific community. The universe remains the ultimate puzzle, and solving it represents one of humanity's greatest challenges. As we continue our cosmic journey, we must remain engaged and curious because every revelation brings us closer to understanding the vast marvels of the cosmos. As we delve deeper into the mysteries of the universe, the role of emerging technologies and international collaborations becomes increasingly critical. One of the most exciting advancements in astronomical observation is the development of extremely large ground-based telescopes, such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT. These instruments, once operational, will have the capability to observe distant galaxies and exoplanets with unprecedented resolution. Their massive mirrors, each spanning several tens of meters in diameter, will collect more light and allow scientists to peer further back in time than ever before. In addition to optical telescopes, other types of observatories are also contributing valuable insights into cosmic phenomena. For example, radio telescopes like the Square Kilometre Array, SKA, are set to revolutionize our understanding of the universe by detecting radio waves from the most distant and faintest objects. This global project, involving multiple countries, aims to create the world's largest and most sensitive radio telescope network. By studying the cosmic radio background, scientists hope to gain insights into the early universe, cosmic magnetism, and the formation of the first stars and galaxies. Gravitational wave astronomy represents another groundbreaking field that has dramatically expanded our understanding of the universe. The detection of gravitational waves, ripples in spacetime caused by violent astrophysical events such as black hole mergers, provides a new way to observe the cosmos. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have already made significant discoveries, including the first observation of a black hole merger. Upcoming observatories like the Einstein Telescope and the Cosmic Explorer promise even more detailed measurements, potentially revealing new aspects of fundamental physics and the nature of gravity itself. The study of exoplanets, or planets outside our solar system, is another area where recent advances are yielding exciting results. With missions such as the Transiting Exoplanet Survey Satellite, TESS, and the upcoming James Webb Space Telescope, JWST, astronomers are identifying and characterizing exoplanets with greater accuracy. These missions are particularly focused on finding Earth-like planets in the habitable zone of their stars, where conditions might be right for liquid water and, potentially, life. The discovery of an exoplanet with conditions similar to Earth could have profound implications for our understanding of life in the universe. Moreover, the field of astrobiology, which investigates the potential for life elsewhere in the universe, is gaining momentum. Scientists are exploring extreme environments on Earth, such as deep-sea hydrothermal vents and acidic lakes, to understand how life might survive in harsh conditions on other planets or moons. Missions to Mars, such as NASA's Perseverance rover and the European Space Agency's ExoMars, are searching for signs of past microbial life and assessing the planet's habitability. Similarly, upcoming missions to the icy moons of Jupiter and Saturn, such as Europa Clipper and the Dragonfly mission to Titan, are expected to provide clues about the potential for life in subsurface oceans. As we continue to advance our observational tools and missions, the integration of artificial intelligence, AI, and machine learning in astronomy is becoming increasingly prevalent. AI algorithms are being employed to analyze vast amounts of data from telescopes and simulations, helping to identify patterns and anomalies that might be missed by human researchers. These technologies are improving our ability to detect transient phenomena, such as supernovae and gamma-ray bursts, and are enhancing our understanding of complex cosmic structures. International collaboration remains essential for addressing the most profound questions in cosmology. Projects like the International Space Station, ISS, and the upcoming Lunar Gateway are examples of how space agencies from different countries are working together to advance scientific knowledge and technology. The ISS has provided invaluable data on the effects of long-term spaceflight on the human body, which is crucial for future deep space missions. The Lunar Gateway, planned as a staging point for missions to the Moon and Mars, will facilitate further exploration and research. In addition to these collaborative efforts, private space companies are playing an increasingly important role in space exploration. Companies like SpaceX and Blue Origin are developing innovative technologies to reduce the cost of space travel and make space more accessible. SpaceX's Starship, for example, aims to enable human missions to Mars and beyond, while Blue Origin's New Glenn rocket is designed to support a variety of space missions. The involvement of private companies is accelerating the pace of technological advancement and expanding opportunities for scientific discovery. The quest to understand the universe is not only about solving scientific mysteries, but also about inspiring and engaging the public. Science communication and education play a vital role in fostering curiosity and enthusiasm for space exploration. Planetariums, science museums, and educational outreach programs are helping to bring the wonders of the cosmos to people of all ages. Public engagement with science fosters a greater appreciation for the universe and can inspire the next generation of scientists and explorers. As we look to the future, the challenges and opportunities in cosmology are both immense and exhilarating. The ongoing quest to understand the universe will continue to push the boundaries of science and technology. Each new discovery brings us closer to unraveling the secrets of the cosmos and deepening our understanding of our place in the universe. The journey of exploration and discovery is an endless pursuit, driven by human curiosity and the desire to uncover the profound truths that lie beyond the stars. With each advancement, we step closer to answering the fundamental questions of existence and to exploring the farthest reaches of space.